second lecture, I will present the classical theory of the Giorgi. That I hope I can complete, minus some details I'll skip, but in the 2 hours. And I remind you that not always, but in parts of this section, I will follow the lecture notes of Anceschi-Rebucci lecture notes, something for a lecture he gave at Beijing University. Okay, so let's go back as a little refresher. Let's go back to the minimization problem we were considering. So I look at this minimization problem on a domain U, and you remember, if I would consider simply the Dirichlet energy, we are simply looking at the Laplace equation for the Euler-Lagrange equation, and then you have all the ellipticity theory here. Okay, so the first thing is, what is my equation? Yeah, the first thing is, the first statement I will state and prove is very easy, and then it will go with an increasing level of difficulty. The first one is to say that if L is C2 with a bound on the second order derivative, then minimizers of that problem in H1 or solution to the following Euler-Lagrange equation that we were going to work on. And the one we're talking about is remind you, this is well, I wrote it first in weak form, but this like that equal to 0. Okay, so let's prove that first, and then I will decompose the answer to the Hilbert problem of the Giorgi and Nash into several statements that we are going to prove one after the other. So this first thing is coming from, in the functional framework I gave you, is just a standard variational principle. So you would just consider, you take some W C infinity compact supported in your domain, and then you look at the energy taken at U plus W plus epsilon W, and you just use that it is greater than this, and now by basic Taylor expansion of this term, you obtain, so I use the Taylor expansion plus the bound on the second order derivative of L, you obtain that it is less than L Laplace U plus epsilon grad L grad U dot grad W plus epsilon plus the lambda epsilon square over 2 times the grad U square. So in this term, I immediately bounded the second order derivative of L. You just plug that here. You take epsilon goes to 0. You take W and minus W. This is the standard variational argument. Okay, the second order term will disappear, and you obtain that your minimizer has to satisfy this for all W C infinity compact supported in U, which is the weak formulation of that equation. Okay? So we're going to work on that, and now the theorem really of the Giorgi and Nash with extension by Moser. Yeah.
Just a question. So here you want that the L be convex. No, you want that the.
No, just for that.
But at least be non-negative, right?
I don't think I'm using that because I'm using that this is greater than that. I'm using that I have a minimizer.
Right. Okay.
But I mean, I'm going to add what you just said now. But okay. Unless I miss something, I think in this calculation I'm not using it. So now I'm going to add the assumption you talk about. Now I'm going to use what I called last time H1, H2. So remind you, I mean, I'm assuming that L, well, I said C2. Last time I said C infinity last time. Let's do as I said in the first lecture. And I'm assuming now that the second derivative matrix is bounded above and below. And the main theorem is the following. Now we can formulate things rigorously. If we consider U, H1 of my domain solution to the Hölder-Lagrange equation, that equation, then U is C infinity. Okay, there are parts I will just sketch, but you see that if you attend everything in this lecture and you can redo that, you've solved the 19 problems of Hilbert. You have C infinity, then the rest is just summing the entire series properly, but you're done. So you see, you start from a minimizer, you put all the assumptions on L, the minimizer has to satisfy that, and you get the interior regularity C infinity, and then you prove the analytic interior regularity. Okay, so one remark, actually it's connected to your question, Françoise, is that for that regularity, so for this theorem, the strict convexity assumption is necessary. Here is a very basic counterexample. Let's go to dimension 1. Let's take as a Lagrangian p square minus 2p. Okay, so that's probably the simplest thing you could think of. So obviously here L prime, we are in one dimension, is 2p minus 2 sine p. Let me check I took the same. Yeah, that's fine. So now when you want to try to understand your minimization problem, what does it mean? Oh, and I'm looking at that on the domain. I forgot to give you the domain. Minus 2, 2, for instance. Now, you look at that, and you have just this object, and of course by forming the complete square, you have that it is just minus 1 or 2. What am I saying? 1, yeah, minus 1. Right? All of that is integrated. And so you have a lower bound, and you can check that the minimizer. So what is the minimizer I want to give you? Oh, I left. No, it's here. So the minimizer U is equal to mod u. So that is a well, you have this minimizer. My sentence is that this is a minimizer, and this fails to be regular at x equals 0. Right? So that's a simple example. Thank you. Yes. X. So that saturates, that minimizes that term. So it's easy. I rewrote it in this form so that you can immediately see why this is a minimizer and this is not regular at 0. Okay, and by the way, in the hypoelliptic case, the kinetic case, understanding which degeneracy are possible or not has not even started. I mean, it's something that would need to be studied. There's a whole literature in the elliptic and parabolic case about what sort of degeneracy you could afford or not. But we're not yet there in the kinetic case. Okay, so then as a recall, so just for the sequel, just a fixed notation, I would define in the usual way, if you give me alpha between 0 and 1, I define the Hölder norm as the sum of L infinity plus the Hölder semi-norm, and the Hölder semi-norm is, as always, a sup x different from y in your domain of ux minus uy over x minus y to the alpha. Okay? Just to fix the notation. And another small remark that I won't talk about, when you have, if we are able to prove that my solutions that I wrote, if we can prove that the u is C1 plus alpha, okay, C1 plus alpha just means C1 with grad u C alpha, okay, and so on. I don't want to give you an avalanche of definition, but they are completely transparent. If we prove that, then the Hölder estimate, which I did not include in these lectures, it's a very beautiful theory, but it's a little bit orthogonal to the tools I'm presenting. It's a non-divergent theory, by the way, the Hölder estimate. The Hölder estimates allow to bootstrap, meaning you just differentiate the PDE, and then you would get C2 plus alpha, and so on, and you continue. So you would get to get the C infinity. So we focus on the first step. Okay. So now here is the main statement. Theorem, the Giorgi, Nash, Moser, and that's the main theorem that I will extend, and probably will be next lecture because I want to prove that fully, to the hypoelliptic equations. So if I consider f h1u weak solution to divergence a grad f equal to 0 with a, so a is a function of x, a matrix valued function of x, okay? And what I'm assuming is that a is symmetric, measurable, and a is bounded above by lambda and below by lambda minus 1 for some lambda strict positive. When I say that, again, obviously, I mean it's a ranking between symmetric matrices. What I mean is that it is below the identity matrix times lambda and so on. Then, f is C2 C2, C alpha lock in my domain. And in fact, it's slightly more precise than that with the following statement. So that always will mean, I'm sure it's pretty standard, but it means it's an open U tilde whose closure is included in U, and because we are in a bounded domain, it's compact actually as well. Okay? So it allows to define a distance between U tilde and the boundary of U, for instance. So if I have a U tilde compactly included in U, then F C alpha U tilde is less than F L2 of U, and the constant here depends on your choice of U tilde. I'll explain how, just by the distance. So you have a quantitative estimate. Well, it's more precise than what I write in the statement. We know very well the constant. So I'll get to this. And this would, if we prove that, we have proved everything, in fact. So let me get to that. But first, a small remark here. It doesn't really make a difference if you would have wanted to define F as an L2 weak solution, as long as you're able to perform the basic energy estimate, as long as you have. So what I'm trying to say, as long as you define a notion of weak solution for which you're able to integrate against F and some localization, you would get the energy estimate that we are going to do at least twice. So I'm going to write it. You would get that F is H1 by the equation. Okay? It just turns out that for alpha is given, sorry, it's an there exists, thanks Loher, there exists alpha in 0, 1 so that it's given by the theorem. It can be made explicit. It was rarely made explicit among elliptic people, but we did it because we needed it. But an interesting sub-question, I've never seen anywhere a theorem about proving that there's an optimal alpha and having it. I don't know if that's interesting, but I don't know if someone has been able to do this. So L2 weak solution, you could imagine doing a theorem for L2 weak solution. And everything is explicit. Well, I mean, not every proof is constructive, but there are versions of this proof certainly that are constructive. I'm going to present the proof that follows largely the Giorgi, except for one key step. The first step of the Giorgi, I will follow the alternative argument of Alexis. That's why I quoted his notes, because it announces, it was really the key inspiration for the trajectory arguments we developed in the last 3-4 years. It announces what I'm going to do in the hypoelliptic case. And in the second part, the control of oscillations, I will explain the version of the Giorgi and then the version of Moser and the version of Kruskov, the modifications. Okay, so the next step is I'm going to make the link, and this is the last time I'm going to talk about the variational problem, just because it gives us a nice way to do a first gentle, not too hard energy estimates. I'll give you the main steps of the calculation. Maybe I'll skip some rather tedious detail. So if you consider U a weak solution to okay, so if you look at what this equation 2 star means, so 2 star means if you chain rule it, it means that contracted with the second derivative of U, and that is obviously what I want to call my matrix A. Okay? So if I consider a certain solution to this in capital U, then for any subdomain compactly included, then we have U H2 and f, which is equal to any partial derivatives of u, solves the second problem, which is the one of my statement. Let's call it 3 star here. Okay, so in that statement, like I said, it's the last time we explicitly use the variational structure. So in that statement, the matrix A is taken of that form explicitly. So it's not any monster, it's exactly that. And it makes the last connection you need. And after that statement, we only work on equations of that form. And in the kinetic case, we'll consider toy problems that are hypoelliptic versions of that statement. Okay, so that's the last time we make the connection with the variational problem. So let's do that. So first, the idea is that by localization, covering then in the end if you want, translation, I give you the key steps, and the rest is a lot of technical steps that you can feel with textbooks like Evans or this sort of things. You reduce to proving it for a U solution in a ball around 0 of size 3. Okay, so B3 is just that. And in H1. And then we will prove that the f, which is one partial derivative of u, solves the final equation I'm interested in B1. Okay, so what we need to prove is that u is H2 and f solves my problem. So one way, you probably know if you looked at that, there are several ways to do this. One easy way is to use the difference derivatives. So for h in -1, 1, you consider tau hu, and then I'm just going to give you the good test function. Okay, what is it? It's the difference version of the dxi derivative I'm interested in, that's all. The EI refers to the direction I want to compute f with. And now, if I consider a localization function eta, which is smooth and which is controlled below by characteristic function of the ball B1 and characteristic function of the ball B2, you see what that statement means? It means you have to be above 1 on B1 and 0 outside B2. And actually, you can even take eta equals 1 on B1. Then finally observe that eta to h and to h eta, you can apply to h first or second, will map h1 of B3 to h1 0 of B3. Okay, so if you've never done that, it looks technical, but it's really not hard. You localize, and when you localize, you reduce to B2, but then you might go back up to B3 because of your translations, but that's all. Okay, so we have localized and we have an approximation of the derivative. And finally, this is, you know that uniform bounds on the difference derivative implies the bound on the derivative itself, on the generalized derivative. And you just integrate the equation on u against, so that's the first instance of a localized energy estimate, which plays a key role in all all the lectures. So we'll integrate it against the following test function, W being tau minus h eta square tau h u. So what am I doing really? The localization always comes square. It's always the good way to do it. You will see why, because in Hilbertian space it's a way to split properly one derivative on the localization and no derivative on the localization. That is just ultimately what I want to be my dxu, and that is ultimately what will be the adjoint of dxu. That's all. So ultimately what I'm putting as a test function is exactly what I would need to form a new control on the dxi of the dxi of the equation. Okay, so yeah. So you just plug that in it, and you get. So this is the part where I might skip one line to not lose too much time, but you integrate on B3. You have your W. Don't forget, because of my localization, W is still in H1, not of B3. There's no problem for integrating by part, and actually that is. That is 0. Well, because in fact, secretly, if you put back the gradient, it's just the equation I start from the Euler-Lagrange equation on U. And you now expand that. Okay, this is 0 on the left. You expand it. There's a slightly annoying calculation here, and well, it's just you gradient all the stuff here. You circulate the translation derivative. You use also that gradient and translation derivative commute. And you obtain a control of that form. This is less than. When I do that, it means there is a certain well, let me write the constant here. You get that. Something like that. And that's it. That's the key control. This is an elliptic estimate, in fact, in this guise for our problem. Except that I've really used, so try to do the estimate, I've really used the form of the equation here. What is the matrix is being used in this estimate. Now you relax the parameter here, and you obtain that U is H2 in B1, that's where eta is 1. When you relax it, you will obtain gradient of dxi of u. You can do it in all directions. And you obtain that f is equal to dxi u satisfies the equation 3 star by similar argument. Actually, to prove this second part, you just test the equation. You just test the equation against. Again, where in my test function, yeah, you just test the equation against any W in H2B1. Okay, H2, 0. So that's all. That's what I showed. What I showed here implies the H2. Once you know U is H2, you can define properly that function in L2. And then it's just a matter of reintegrating against the test function to prove that what you would have done formally if everything was C infinity is still valid for this generalized derivative. Okay, so now, like I said, it was the last time we really considered the original motivation of all of that, the 19th problem of Hilbert. So now we forget it and we'll focus only on the elliptic, then parabolic, then hypoelliptic kinetic version of that equation with rough coefficient. That's what we'll do always from now on. And we'll start with the first lemma of the Giorgi. first, let me do a remark. That helped me to understand this theory when I started looking at that like 6-7 years ago. I hope it will help you as well. Trying to obtain some regularity on the solution here is not an easy problem, but it's good to try all the naive things you could think about. Because A is only measurable, the H1 estimate is clear. The H1 estimate, well, you just integrate against, for instance, U or even U times the localization function, whatever we call it, maybe phi square. You will obtain estimate on the gradient of U integrated. That's fine. To go above H1 to H2, you have a problem because you can't differentiate the equation. Everything would hit the matrix, which is crazy, possibly crazy oscillating. The other thing, okay, that is more or less trivial. So this is not, it is not a sort of induction on the energy estimate, which is usually what you learn in PDE 101 at university. The second thing is that, and that is more subtle, this is not solvable by a perturbation argument. This is really the strength of the Giorgi-Nash-Moser theory. This is not a perturbative theory. It is not about saying that A is close to something. You could try to argue that A is L infinity close to something, but even that, it's not clear it will help you, because it could still oscillate like crazy at all scales. Okay, this is what. On the other hand, you gain something, paradoxically, from having an A that oscillates at all scale. And that is what, for me, was most counterintuitive, because you usually don't do that when you don't deal with rough coefficient, is that the form of the equation is scale invariant. And that has consequences that are extremely deep. Because the matrix A is assumed to be only L infinity, any sort of zooming, dilatation, everything you could do will preserve the ellipticity bounds on A, what I call ellipticity bound, the bound above and below. So we are going to prove some inequalities that are scale invariant as well. And having an infinite family of inequalities has a lot of rigidity properties. Okay? So we lose a lot of things we know how to do, but we gain something with the fact that the class of equation, by class I mean that if you dilate, rezoom, rescale, the A will change but will keep the same assumptions. Is that clear, right? What I mean? If I, for instance, consider the matrix like A plus A of x naught plus lambda y as a new function of y, okay, if A was a smooth function, I would be changing the regularity with this lambda. Here I'm changing nothing. And in this approach, it is very natural to always try to establish only scale invariant properties. And that will lead us to the second observation in the first lemma of the Giorgi, because everything has to be scale invariant, and there's one thing that is not respecting the scale is the Sobolev embedding. The Sobolev embedding is a collision of scale between surface and volume, if you want. And this is this collision of scale that will produce the first lemma of the Giorgi. So, how did I call that? Well, maybe. Second item. So, first lemma of the Giorgi. So consider the following notation. F plus will always mean max of F and 0. This is the positive part. As I already used, BR always means ball centered at 0 with radius R. And then the lemma is the following. So, under the same assumption as above, so let's say I'm considering H1U. I didn't say in my remark, but it was also obvious Of course, in dimension 1, you wouldn't need that lemma actually, because it's much simpler in dimension 1. But the higher the dimension, the less H1 would give you in terms of integrability. So controlling my C alpha norm, which contains L infinity, you can see that it's highly non-trivial. Even the L infinity bound is non-trivial in high dimension. So F H1's weak solution to this equation that I call 3 star, with A as before, with the bounds above and below, measurable with the bound and above and below. Then, and I will do it on B1, sorry. Then there is a delta, and it depends on lambda and the dimension, so that F plus in L2 of the ball B1 less than delta implies F less than 1/2 almost everywhere in the ball B1/2. So you see, it's a gain of integrability. In fact, because the problem is linear, I'm going to formulate it like that in a second, but this is the original way that Giorgi was thinking about it. Moser later, of course, reformulated it as a linear bound between L infinity and L2. And maybe some sanity check. If you would, maybe the last time I make the connection, you see that for the it would imply that the minimizer U in the Hilbert formulation would be in, so H2 we already proved that, but it would be in H2 inter, and then we'd have proven that the gradient would be in L infinity lock, right? Because the gradient is F. F is each coordinates of the gradient with an explicit bound. Okay, so let's prove that. So this theorem has something reminiscent of many other theorems of that decades, the 50s, 60s, 70s. It has a nonlinear scaling that is reminiscent of the KEM theorem, the Nash-Moser embedding implicit function theorem, and in general Newton schemes, theorems based on Newton schemes. So there is a super geometric convergence in the constant that makes the theorem works. I've done all my remarks. Yeah, maybe I'll give the remarks later. Yeah, okay. So there is this double exponential or super exponential aspect. We'll see in a second that the statement remains true for subsolutions, but I'll state it more precisely later. And that's all. Yeah, that's all my remark. Proof. So the idea is to do the following. I'm considering, for instance, B1, where I have a solution, and then I will consider a sequence of radiuses converging to the ball B1/2. Okay. And my target is to prove that in the ball B1/2 I'm below 1/2, starting from a solution in B1. And I want to perform an iterative argument. So in the De Giorgi version, the iterative argument is performed on the following object: an energy Ek, k greater or equal to 1, which is simply integral on the ball Brk of f minus e little k plus squared dx. So if you look at the picture, it's really very simple. You want Rk to be something that converges geometrically back to 1/2. So you take 1/2 plus, plus 1/2k plus 1. And I realized I started at k equals 0 anyway. Okay. So then that's consistent. R0 is 1. R infinity is 1/2. So that's what I want. And for E is a level at which I cut off things. So I want that E converges upward to 1/2. So I'm going to take the little e to be 1/2 minus 1/2k plus 1. So E0 is equal to 0 and E infinity is equal to 1/2. So look at what, there is a plus, don't forget it. Look at what that object does. It just collects and measures the mass in the upper level set above 1/2 minus some small stuff. And it collects it in the L2 norm. And now the goal, so the claim is the following. The claim is that we have the following inequality between the energy Ek and Ek minus 1, so for k greater than 1. And this is for a constant C, strict positive, and importantly for a beta strictly greater than 1. That is the key aspect. So we are going to prove the claim, but first I want to show why the claim implies the result. Everything is in this beta greater than 1. Because the beta is greater than 1, the constant becomes immediately irrelevant. So look at what it means. So a claim implies the lemma. Let's prove that. So you just resolve the induction. It's neither very hard nor very interesting. So I'm giving you the formula. Okay, you reapply onto Ek minus 1 and so on, and you get the following. You just get Ck plus beta k minus 1 plus beta squared k minus 2 plus plus bk minus 1. And then you have the first E0 term to the power beta to the k. So this is what I meant by super exponential or double exponential, whichever way you want to call it. This is characteristic of the error in a Newton scheme that you've done in high school. And this is also the reason we can prove the KAM theorem in dynamical system. It's what makes the Nash-Moser theory works and so on. So that will go incredibly fast to 0 if E0 is small. We just have to make sure this is not able to compete with that. So here you just check that this exponent. So it's a simple calculation. You can observe that it's beta to the k times the derivative of a simple geometric series. And you obtain simply that it's k plus 1 over 1 minus beta. The calculation is not totally uninteresting because you see how it blows up when beta approaches 1. And then here you have a square. And you see that provided beta is not approaching 1, it's less than beta to the k. So you obtain that Ek is less with a universal constant to C E0 to the beta to the k. So if E0 is small enough, then this would be less than 1, and that will go extremely fast to 0. Okay, and that concludes the proof, provided we have the claim, because then okay, then you have so then that goes to 0 very fast, but in fact E0 is simply F plus on the whole ball. So we assumed, my statement is somewhere, yes, we assumed that it was less than delta. I said there is a delta, now we see where the delta comes from, it has to be 1 over c. And because it goes to 0, we have that L in E infinity, which is the ball 1/2 F minus 1/2 plus squared is equal to 0. So F is less than 1/2 almost everywhere. Okay, so now how do we prove the claim? It's the combination of the basic energy estimate and the Sobolev embedding. So, proof of the claim. So we want to show the following. The first step is the energy. It's a localized energy estimate. I claim that for any phi C1 compact supported in B1, then I can control a localized H1 dot norm, if you want, by L2. So that's an elliptic estimate. We call it energy estimate in this context. That's controlling locally an H1 by L2, because we have an elliptic equation. That's my ellipticity constant on the matrix. That's the L infinity norm on the phi. And then I have an integral of F plus square. And this is important. It's integrated on B1 intersected with the support of phi. Okay, so let me call that equation 1. So to prove that, proof of that elliptic energy estimate, we just integrate the equation on F against localization squared, the localization function squared times F plus. So that's my test function. Okay, I'll try to call W always a test function. So what do we get? So I get 0 is equal to, so I do one integration by part, which is legit because, let me write it first. I do an integration by part, which is okay because of compact support of phi. So I get minus A grad F composed with phi, grad of phi F plus, no, yeah, there's no square here, so it's here. Yeah. And now I expand, but the way I expand, I write that as phi times phi F plus. So I put the gradient here or here. And I get that it's minus A grad F. The first one would give grad phi times phi F plus minus A grad F grad phi F plus phi. Okay, so you can observe that because I'm restricting everything to the support of f plus, I can add f plus here. Okay, if it looks like I'm cheating you, just try to check this following thing, which is, of course, very simple. If you do characteristic function of f greater than 0 time gradient of f is the same as gradient of characteristic function of f greater than 0 f. It's done in the Bresis book, for instance, many books. You're not allowed to swap a characteristic function all the time. This one works because precisely, well, the intuition is that when the gradient would like to hit the characteristic function and produce a Dirac mass, well, conveniently at that time f is 0. So it doesn't produce any other bad terms. Okay, so, and now I want to, in this term, no, sorry. So in this term, I want to, okay, let me check so that I do it in the right order. Yeah, so I'm keeping that one. Let's not touch that one. And in this one, I want to reform a phi f plus here by force. So I have this one that I keep as it is. And now I have minus a gradient phi f plus, gradient phi f plus. And of course, there's a term which I'm not accounting for here, which is plus dA grad phi f plus, and should be almost there. So that's the one I'm interested in. And now the difference of these two things, yes, it works. And you look at the difference of these two things, when I will expand that, one will kill this one exactly. And I get, let me skip a line because on the blackboard it's really not nice to write lines and lines of equations. So you write, I expand this gradient, I kill the grad f plus with this term, and I get simply just the clean estimate integral a. I don't really need to tell you the domains because it's localized by phi anyway. That is less than integral of a grad phi. Sorry. I'm doing something. The A is A grad phi f plus, scalar grad phi f plus. And the second one is A grad phi scalar grad phi f plus squared. Yeah, there's no factor. And now I use on the left the lower bound on A, on the right the upper bound on A, and I just get lambda minus 1 integral on B1 of grad f plus. What was the form? Sorry. Oh, let me just keep it exactly the way I told you. I'm writing exactly in the form star. You deduce what I call star. You just use the upper bound and the lower bound, right? On the left-hand side, the lower bound gives you a bound from below by lambda minus 1, what I wrote. On the right-hand side, an upper bound by lambda, what I wrote. So you put back the lambda minus 1 and you have the lambda square. And I just took out the grad phi in L infinity. That's all. So you have immediately that. The second step is the Sobolev embedding. Which is the source, like I said, of the collision of scales. So, in order to see things, we need now to take little characteristic functions that are smooth, that are nicely connecting between one layer have the time to decrease from 1 to 0 between two layers, and then or 0 here. Okay, so the image is simple. It's 1 on one layer, decrease, and 0. So let's define that. We take phi k C infinity compact supported in B1 so that, so I want phi k to be 1. Let me make sure I get the index right. Let's say k is greater than 1. Phi k is 1 on bk. Phi k is 0 on bk, so it's brk. It is 0 on brk minus 1 complementary. So don't forget the radiuses are reducing. Right? So it's 0 outside the larger one. Okay, and and also because my radiuses are converging geometrically, it's not hard at all to get an estimate on the gradient. So you can either check that you could build it, or if you want a much quicker way to do it, you can just build this phi by scaling. And this will immediately prove that the gradient satisfies a bound of that form. The key point is the 2 to the k. Okay, because it's proportional to the width of the gap. Okay, so now we have localization functions on these reducing balls. I'll finish that proof and then we can have a 2 minutes breaks. And then the observation is that f is a solution, which implies that f minus ek is a solution. Why? Because ek is a constant. The PDE is linear. It starts with a gradient, so it doesn't cease the constant. So we can apply the claim, which is, still written here. So we apply the claim star to f minus ek and the function phi equal phi k. Okay, so you get simply integral on B1 of gradient phi k. This could look technically bad, but if you look at the picture, as always, it's actually very intuitive. Here it's the L infinity bound on your phi k, and times the integral on phi k square f minus ek plus squared on B1. Oh, well, I already dropped, sorry. I already wrote it as B1 sup of phi k. That's fine. Just because phi k is L infinity. Right, okay. The other thing is that ek you remember what it was? It's just the amount of mass above ek in the ball rk. That is less than, because phi k is 1 on that ball, it is less than phi k f minus ek plus. Do I put? Yes, I put the square around everything in B1. I'm just spreading a little bit by a function that is smooth. Initially, I have the characteristic function on that. I bound it from above by the phi k. Okay. And now the proof is more or less finished. What remains to be used is a way to connect that back to EK. And that's the Sobolev embedding. So that's what we are going to use now. So I'm going to skip one thing that has absolutely no difficulty. The fact that the embedding is better in dimension 1 and 2, so my exponent is not good enough. Okay, but I'll do as if d is greater than 3 to make just the writing simpler. So d greater than 3, otherwise even better, simpler. I'm just saying that in dimension 1, H1 embeds already in L infinity, so why are we doing that anyway? And in dimension 2, it almost embeds in L infinity, but you could always do what I'm doing with an exponent in between 2 and L infinity, and it will still work. It's just very annoying to write, so I'm just going to skip that. And I'm going to define P to be 2D over D minus 2, which is the Sobolev embedding exponent, and write that we have phi k f minus ek plus lp over b1. Did I put with a square? Yes, I put with a square. Less than a constant which, let's call it C sub for Sobolev, so that you really remember where it comes from. Gradient phi k squared L infinity b1, and then, sorry, where is my, no, at that point I skipped one term. Let me first write it. Here I would have integral of gradient phi k f minus ek plus squared dk. So that is just the Sobolev embedding in B1. You have a constant, which you can find even explicit form of this constant in the literature. And now I bound this term. So what do I get? I have the square of the Sobolev constant, and then I have I'm using my claim star. You remember where is it? Yes, it's still here. I'm using the claim star to get, it's bounded by lambda square. It's bounded by the gradient of grad phi k squared L infinity, but this is bounded by 2 to the 2k. Okay, we checked that before. And what do I have else? There is an absolute constant in front of everything, okay, that I don't really want to discuss. That plays absolutely no role in the convergence of the scheme. And finally, I have integral of f minus ek plus and b1 intersected with the support of phi k. And squared, sorry. Okay, so first let's check that here we have an energy term, an ek term again, so it's not very hard. I'm just saying that on the support of phi k, well, the support of phi k by assumption it's included in the ball with the previous radius. We have phi k minus 1 equals to 1. So, why do I say that? I don't even need that, sorry. And then f minus ek plus is less than, so the phi k, yeah, this one is less than f minus ek minus 1 plus. Is that okay? So what I'm doing two things. I'm using that this support will impose that you're actually secretly inside BRK minus 1. And I'm using something else, which is that if I take the previous level, I'm widening the gap. So I can only increase things. So I'm actually bounding the whole of that thing by EK minus 1. So we're almost there. Look at what we started from. it's not far from EK, but it's actually better because of the small gain of integrability above L2 by the Sobolev embedding. Okay, so last step. We have now that EK, which is the integral in BRK f of, yeah, my indices are correct, yes. That is less than integral of phi k f minus EK plus squared on D1. Okay, same trick. I'm squeezing the localization function because it is 1 on that domain. And now I'm doing the Hölder, I'm using Hölder inequality in order to use the LP bound. So I'm going to say that it's less than phi k f minus EK plus LP, the P I've just defined. Everything from now on is integrated on B1 because I've localized. And then I have the rest, which is the integration of 1 on something, so that I give you what it means, is just the measure of phi k f EK plus strict greater than 0, and then the bound is the conjugate Sobolev exponent, which is 2 over d. Why? Because I've applied Hölder with, so my two exponents are, where are they? P, yeah, P, which was 2d over d minus 2, and P star, which is d over 2. Is that correct? So d minus 2 over 2d plus 2 over d. No. It's because I've squared everything. Yes, it's because I have forgotten to square everything. Sorry. So this is Hölder, but the exponent here is d. Okay? So you check that this is indeed...
and you have the 2 of d minus 2 divided by d, right?
Right. And I have a factor 2. There's no factor 2? No, what? I get 1. Yes, I start with L2. Thank you, Laura. Yes, good. So this works well. Well, actually, any gain would work, but it's nice to keep the exponent because you see exactly how things depend on everything. And now, this by Chebyshev will allow us to control a little bit more power of the energy. Okay, so we have EK bounded by that, and that object now we know is bounded by everything we've done before, and we'll apply Chebyshev on the other part. I don't know if we... No, we can't do that. So the Chebyshev part is simply the measure of phi k f minus EK plus strict greater than 0 is less than... So here you have to remember how the level sets are distributed. It's actually less than that. So if you don't do a drawing, it will give you a headache, but on a drawing it's very simple. So the supports are increasing, so that's why, decreasing, so that's why I can do the replacement here. The key point is that between EK and EK minus 1, you can exactly squeeze a 1 over 2 to the k plus 1, that's all. That's why you can have this ranking. And now that I have something that is non-zero here, I can do Chebyshev, the Chebyshev inequality, to deduce that I have two this constant 1 over the square of this constant, so 2 to the k plus 1, and then integral on B1 of phi k minus 1 f minus ek minus 1 plus everything squared, and that is just 2 to the 2k plus 1 ek minus 1. So overall, I have proved that, let me summarize the final inequality, I have proved that ek is less than an annoying constant ck ek minus 1 to beta, where explicitly beta, so I'm giving you the values and you check them. Beta is 1 plus 2 over d, and the c that is here, if you want to calculate it, you get just c to the k is c sub square lambda square. I had my minus c0, they play 0 role because they are not even going geometrically. And then you have 2 to the 2k, and then you have 2 to the 4 k plus 1 divided by d. The 2 to the 2k was from the claim star. This one comes from powering this to the 2d. That's what it is, but it has the form I claimed, and then you can conclude. Okay, so before I go to the second lemma, because in order for you to digest this first one, let me give you the way Moser formulated it. Should we do a 2 minutes break or? Yeah. So I just finished the proof by Giorgi. Yeah, and I couldn't remember the name, but indeed that was called Caccio. There must be 2C. Caccio-Poli, maybe 2P or 2L. Anyway. Oh, pas de H. No H. Okay. Caccio-Poli. Okay, some. Okay. But I mean, I think today we would call that an energy estimate. So very soon after, there is the viewpoint of Moser that was published, as I mentioned in the first lecture. So the proof of Moser of the first lemma of Giorgi is very similar. I don't want to pretend it's very different, so much so that what I presented is often called the Giorgi-Moser iteration. In particular, in geometric PDEs, like minimal surface equations, it's often called the Giorgi-Moser iteration. But there is one thing that I want to emphasize in the Moser viewpoint that was present in Giorgi but not really highlighted in the original paper, is that actually the previous lemma only uses star. So that's the first basic remark. Actually, if you really look at it, I've only used the energy estimate, and the Sobolev embedding is independent from the equation. And the energy estimate, the Caccio-Poli estimate star, which is still valid for sub-solutions. So F, so that you have that. Okay, so if my proof is still there, but it's not still there. It's not still on the blackboard. Yeah, it is still on the blackboard. Here is it. So you check that if I would do this, actually the whole proof carry on. That's a very important remark. And it's not that surprising. I mean, the operator has a sign, in fact. We're using the fact that it's a negative operator. But now, if you combine that remark with the following, if I have a capital phi nice function, so smooth if you want, or let's say at least C2 on R, on whatever, on R plus, this is enough, with phi prime and phi prime prime non-negative, then a very standard result of elliptic theory is that F subsolution will imply that phi of f is also subsolution. Why is that? It's an elementary proof. It's because if you expand that, you get that it is simply phi second f of A grad f grad f. So that is non-negative, and that one, you know what it is, plus phi prime f, plus phi prime f of divergence A grad f. So that is non-negative by the equation, that is non-negative by the sign of the matrix. This is a positive matrix. So you still have a subsolution. And the way Moser writes the iteration is slightly different. He considers as the main term on which we induct not Ek, but something else. Let's call it Fk. So Moser defines Fk to be integral of f plus Lpk of b rk. So the b rk are the same as before, the same as for the Giorgi. So yeah, same as in my picture that I've erased. The pk now are an increasing, geometrically increasing sequence given by 2 times 1 plus 2 over d minus 2 to the k. As before, I'm doing things for d greater than 3, but there will be an equivalent statement. And so you see that p naught is 2, and of course p infinity is infinity. So we connect nicely L2 to L infinity. So then what Moser will do simply is to prove that so the claim, the equivalent of the claim of the Giorgi becomes in Moser version that Fk plus 1 is less than a constant over 2 to the pk, 2 to the pk. Well, I could have given you a whole constant, but this constant will include the Sobolev constant and everything. Now, this is a linear, in contrast with the Giorgi, the relation between Fk plus 1 and Fk is linear, but what is interesting is this nonlinear way you scale the power of that constant, and now when you resolve, you get that F infinity is less than the Cauchy product of all these things. So you get the product of all C, well, let's call it 2C to the 2 over pk for k greater than 0, F0. So the proof of Moser has the advantage of showing in a slightly different way, representing things differently, that it's really a linear estimates between the L infinity bound on the 1/2 ball and the L2 bound, because F naught is simply the L2 bound on B1. And that Cauchy product is converging because of the geometric growth of the pk. You can do it, you can log it and check that if you log it, the series is summable. The proof of that doesn't require Chebyshev, but is still completely based on the Sobolev embedding. So the proof, so you just use the energy estimate. I don't need to spend that much time because we did most of it. With the same notations as before, you get this bound in L2 less than 2 to the k fk to the pk over 2. So why do you have that? So look at it carefully. It's because I have applied the energy estimate to this, which is a subsolution. F plus is a subsolution, and now if you power it to a power strictly greater than 1, yeah, sorry, I'm going a bit fast. Let me give some sub-steps. F plus is a subsolution. Okay, so F plus subsolution, it means simply I have that. If F is a subsolution, F plus is a subsolution. It's the same trick as before, because you can swap characteristic of the function greater than 0 with the gradient. Okay, so that is easy. Now, if F plus is a subsolution, F plus to the pk over 2 is a subsolution as well, because pk over 2 is strictly greater than 1. So that's the core idea of Moser. So you apply the Cacciopoli estimate to that subsolution with this localization function. What do you get then? Well, you get the integral on B1 inter the sup and blah blah blah, and you would get f plus to the pk over 2 times square, right? And then 1 over 2. And you have the constant. There was a certain number of constants and a 2 to the k. And now you just recognize that here the support will give you the BRK. And that is just f to the pk. So that's why I'm recognizing fk is the LPK norm. And in order to fabricate the pk norm, I have to divide the power here by 1 over pk. And so it creates a pk to restore it. That's all. Okay, so this is what becomes with the energy estimate when you apply it to all these sub-solutions. And second thing, you apply the Sobolev embedding. And the Sobolev embedding will exactly tell you that you will control the F plus in a pk that is multiplied, so let me write it correctly, a pk 1 plus 2 to the d minus 2 of brk plus 1 times less than this, less than that. Sorry, I don't want to write too many more technical terms, but I'm just saying this is the H1 norm. It controls from below a better LP term. And the gain of integrability by the Sobolev embedding iterates to give this geometrically growing sequence of exponents. And therefore, you have the final stuff. Okay, so that gives the gain of integrability. Let's go now to the second lemma of the Giorgi. Yeah.
Explain a bit more. So this gain you got from the Chebyshev, where is it? I'm lost. I mean, you don't do it, but what is the equivalent there?
No, it doesn't appear in this form there.
There is no counterpart?
No, not of the Chebyshev part. Moser tells you that really, because if you're able to increase the integrability at one step from L2 to L2 plus epsilon, you can just reiterate it because the equation is satisfied. I mean, the sub-equation is satisfied by all the powers of f. It relies on another observation, really. But I mean, the proof are still considered philosophically equivalent, but they're not exactly the same.
Is this a sort of ultra hypercontractivity?
I don't know if you could interpret it like an ultra-contractive.
For example, if you consider a parabolic problem, then we may also have this growth of integrability.
Yes. I'm going to talk about parabolic problems. It depends how you define ultra-contractivity. So that's for you to tell me. If for you being ultra-contractive just means you instantaneously, in strict positive time, you go from L2 to L infinity, yeah, why not? But for me, ultra-contractive means more than that. It means also something on the constant, but it depends on...
But maybe if you...
For me, that's regularizing, but...
The growth of the constant might be interpreted, and if behind that there's some Loher inequality behind the elliptic structure, maybe it can be reinterpreted as some growth of this one.
So the main proof I didn't talk about for the moment, the Nash proof doesn't go through the gain of integrability. It doesn't use log-Sobolev inequality because it was not invented at the time of the article. But he uses for parabolic equation, the derivation of f log f. That's the beginning of the article of Nash, famously. And he uses the control on the Fisher information. But he doesn't use the log-Sobolev inequality per se. My intuition, I could be wrong, but my intuition is that, be careful, this is really regularity theory. And I don't expect it would give you the sort of sharp constant you like for ultra-contractive semigroups. The constants are likely to be a mess. It's really a regularization, just.
But the hypercontractivity also is a regularization. And it says how you regularize, but...
Actually, I'm not sure I know exactly a clear definition of it. But for me, there is contractive in the name, and for me, contractive means an assumption on the constant in the semigroup decay.
Yes. Sorry, not what it gives. Okay, maybe we'll talk about it.
But because otherwise, any parabolic equation is hypercontractive then. And,
may I ask a question about the intuition behind all this computation? Because at the very beginning you mentioned that this result is related to this scaling variance of L infinity. So how you can say interpret this scaling variance in all this computation?
Yeah, I think I wrote some. Yeah, absolutely. So the first thing to say is that I wrote it before. Good point. The first thing to say, let me make a remark, is that the best way to it's a first pre-answer to your question. The best way to formulate what has been proved is to say something like that. If you want to really make it scale invariant, you would like to say that instead of integrating on B1, let's say you bar the integrals, meaning actually you do integrate on integrals where you've normalized the measure, and then you could go to any ball centered anywhere and of any radius. And if you'd have that this is less than delta, then you'd have that f is L infinity BR over 2. And in fact, less than 1/2, sorry. And in fact, now that I presented the viewpoint of Moser, you have an even better, I think, relation for the intuition, which is that everywhere you look at every scale, you have a universal connection between, and you could center it at any point you want. So this is completely scale invariant. Oh, sorry. I mean that. When I do that, it means I normalize the measure. Sorry, and that when you can, but it means nothing in L infinity. So that is a relation at every scale that is much stronger than what we do usually for smooth coefficients PDE. See what I mean? It's actually an infinite family of inequalities that we've proved. And we proved it because we used no regularity information on the matrix. This is the only way you could prove something like that. We used the bounds below and above on A that are completely preserved by changes of scalings.
It's related to maximal functions or things like this?
That I don't know. I don't know if there's a proof or a connection to maximal functions. Yeah, no, I don't know. But it's definitely related to not exploiting any regularity on the coefficients, so that you make things completely scale invariant. Yeah, that I said. Sub-solution. Yeah, so there's a connection to so that's the Moser viewpoint, and Nash. In Nash, you don't see the gain of integrability per se. In Nash, there is another viewpoint that I really don't have time to introduce here, is directly bounding pointwise the fundamental solution. So Nash starts like that.
Yeah, but Nash doesn't. It seems that Nash starts from things that are already an infinity, if I'm not mistaken. Yeah, I'm not sure that Nash needs this first step. I mean, I think it starts from functions which are already bounded.
I think his final theorem is for weak L2 solutions. I'm pretty sure, actually. But okay, to be checked. Yeah, tell me if he does completely skip this step, I'd be surprised. So, second lemma of the Giorgi. So, as you will see, next class, maybe Wednesday, the first lemma, the extension to kinetic equations, is interesting. But it's not what I will spend most of the next 2 lectures on. It's interesting. It's a consequence of combining the original ideas of the Giorgi and Moser with averaging lemma. I mean, to summarize brutally, the averaging lemma will help to bridge the gap between elliptic and hypoelliptic operators. The second lemma requires more novelty in the end, and that's what I will spend a lot of time on, because it really pushed us to understand how to construct trajectories and even critical sharp trajectories to capture the Hermander hypoellipticity of operators. Okay, so, and in order to make a link with the next part, the proof I will present is this proof of Alexei in the elliptic case that already has a flavor of trajectories. So now this second part is concerned with regularity, not just integrability, and the viewpoint of the Giorgi. So the viewpoint of Nash is to look at the fundamental solution, but the viewpoint of the Giorgi is to say, well, because I can't differentiate the equation, I don't want to use derivatives. So what can I capture in terms of regularity if I don't use derivatives? What I can use is the oscillation. It's a sort of pointwise measure locally of regularity. You want to measure pointwise the modulus of regular continuity locally. So the idea of the Giorgi, that will take a couple of lemmas to prove, is the following. He wants to say that when I scale from, let's say, ball 1 to ball 1/2, it could be another fixed factor, I want to see that the oscillation is reduced. So what do I call the oscillation? Oscillation in ball 1 of f is sup f minus inf f. Of course, it's fundamental that we've proved that by the previous lemma that everything is an infinity. So we can now consider the oscillation everywhere. And the goal of the Giorgi is to prove that there is a universal lambda so that the oscillation in B1/2 is slightly reduced as respect to the oscillation in B1. Okay, so the lambda factor is strictly less than 1. So that's the first thing we're gonna prove now. If you do have that, by iteration, and here it's important again that everything is scaling invariant, you reapply that zooming, 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 and you'll obtain the Hölder regularity at the point. And you can do it everywhere. Okay, so the goal will be to prove this reduction of oscillation, as it's called in this area. So let's do that. Okay, maybe first a little a statement a little more rigorous than what I said. So F, if I consider F a solution, and here I want to emphasize that it's not okay to take sub-solution only. It needs to be a solution from above and below for that statement to be correct. Let's have to be a solution of, well, my usual equation, right? On a certain ball. So it turns out that you need to ensure that you have a solution a little bit around it. And then my picture is correct, but I will really consider the oscillations in these two balls. Then, with A, as always, measurable, symmetric, and A bounded above and below as always. Then there is a constructive lambda in 0, 1, depending on the capital lambda and the dimension as always, so that, and nothing else, it only depends on that, so that oscillation f in B1 half less than lambda oscillation f in B1. Okay, so the first thing is that let's prove that it really shows the Hölder regularity. Which means the last thing to prove will be that, and then we have the full 19th problem of Hilbert. So if F is a weak solution to my problem as before, on some open domain, then there exists an alpha in 0, 1 as well. That is explicitly, I'm going to write it's minus log lambda over 2 log 2, but we're going to write it in terms of lambda, so that F is Hölder locally in my open. So let's prove that. We're going to prove that this lemma implies the corollary. By the way, there's a beautiful application of the scale invariance law. I hope I'll come to that in the end. That weaker form of Harnack inequalities are rigidified by the scale invariance. This is something I've used a lot. I mean, it really has consequences that are, for me, surprising, not super intuitive. So let's consider. So I have my domain U like that. Let's consider a U tilde as always compact embedded in U. And therefore, we have a distance, d, let's call it d naught, a distance between U tilde and the boundary of U. Okay, so that would be this, for instance. And we rescale. Let's define f tilde of y to be f of x naught. We consider, sorry, I forgot to say, and I take x naught in that, of course. So I'm considering x naught plus d naught, let me try to get a constant right, y d naught over 4 So over 2 would be enough to not approach the boundary, but if you ask why I put over 4, it's because in my statement it's purely arbitrary. I have to be a solution up to B2. That's all. That's why there is a 1 over 4. And then I will define a sequence of solutions where G1 is F tilde and Gk is Gk of y is Gk minus 1 of y over 4. With each iteration, I divide by 4. So just observe now that Gk, each of the Gk is solution to the same elliptic problem with the matrix AK. AK of y is simply A of x naught plus d0 over 2, and then I have 1 over 1/4 k minus 1. I mean, I hope my indices are correct, but anyway, that doesn't matter that much. And of course, this matrix still satisfies measurability and the bound above and below as before.
It's y, d not y.
Yeah, sorry, I forgot to put y. Indeed. Absolutely. So, so I have the same assumptions, and I'm just going to apply the lemma to each Gk. So the lemma to Gk gives lemma applied on Gk gives us, well, oscillation Gk, let me write it in the variable of Gk, and then I will unfold everything, less than lambda oscillation of Gk in B1. And now that means oscillation of F tilde in, so check the exponents when you read your notes, because I mean, doesn't, you can see that it will work. I mean, I'm trying to write the exponents correctly, but so of course, I forgot. What am I saying? Yeah. So you will, since I divide the ball by 2, you can cascade. Okay, each time you appeal to the larger ball, and you deduce from that the following estimate for where is it? No, there's no 4. There's lambda to the k minus 1 oscillation of B2 of A tilde. So I've applied repeatedly that from a ball divided by 4 to the k to the ball B2. And the last one, I don't really want to know what it is. The oscillation is a sup minus an inf, so it's twice the L infinity norm. F tilde is just a translation dilation of F, so it's bounded by L infinity norm of F in U, for instance. And now for this one on the left, you deduce that it's an oscillation in a small ball. You deduce that if you take x, so x near x naught, you will see in a second why it's finished. You take x near x naught, so that x minus x naught is between 1 over 4k and 1 over 4k minus 1. Okay, you have a layer of annuli. I can always pick up a point and decide what is the good k to have that. Then, let me keep it here and write it here. Then you deduce that So here I'm using the oscillation of L tilde, F tilde, to say that it's twice 2k minus 1 Fn infinity. Now I'm using what I know about x minus x naught to say that it's less than 4 to the alpha lambda k, and I have a big absolute constant that this doesn't depend on k, x minus x naught to the alpha. Okay, look what I'm doing here. I'm just saying that x minus x naught to the alpha would be greater than 1 over this power. So I put it on the left, and it's greater than 1. I'm just making it appear by force by paying a huge constant. That's all. And that's it. I'm now making sure that this is 1 by saying that I pick up alpha to be minus, so you just want that to be 1, so you log it and you find that alpha is minus lambda over 2 log 2. That's all. So you have a choice of alpha. And with that choice, you get for all x, because I've chosen an arbitrary annulus, you get for all x close to x naught a bound by the Hölder semi-norm of f by the n-infinity norm. Okay? So, this is just telling you that a geometric reduction of oscillation, when you geometrically scale your variable, gives you a Hölder regularity. It's an alternative way to formulate the Hölder regularity. Now, I'll just take 5 minutes to give the beginning of the next steps. The next step is to prove the reduction of oscillation. And here, the idea is to reduce it to a step that is super interesting in itself, and that is, in fact, is the core to the Harnack inequality as well. It can be reduced to the following lemma, which has different names in the literature. I think I can give it to you and explain. The argument is trivial. Decrease of the max or increase of the mean, sometimes it's referred like that. Or, and that's the name I prefer by far, it's a measure to pointwise estimate. So what does it say? It says the following. I will want a solution in B2. I will ask, I think this is the least trivial estimate in the whole the Giorgi paper. So I have a solution here in B2 that is less than 1. Okay, I ask that this solution in B1 has some mass where f is less than 0. You see what I mean? There is an amount of measure where f is less than 0. And the conclusion is that in the smaller ball B1 half, here f will be in fact secretly never reaching the max you've allowed initially. Okay, so the amount of mass below 0 forces f to be not touching the max in the smaller ball. Because intuitively the problem is that f needs a lot of, I can't say time because there's no time, but it takes some effort, let's say, for the function to go back from 0 up to 1. So that is the idea in this statement. So let's formulate it properly. I consider f less or equal to 1 being a sub-solution in B2. So remember subsolution means that. And I suppose that there is some mu strict positive so that the measure B1 inter F negative is greater than mu. I have some mass below 0 in the intermediate ball. Then there exists a lambda in 0, 1 so that, and it depends as always on the dimension and the capital lambda and nothing else, so that the sup in the smaller ball, these are always essential sup, and by the way, okay, I mean it's always almost everywhere, is less than 1 minus lambda. Okay, so I think what I have time to do is to tell you why it implies the decrease of oscillation, which is really extremely simple. And then the main statement we're going to prove at the start of the next lecture, which is really the first step into where I will start discussing the extension to the hypoelliptic case. So how do you deduce proof of measure to pointwise, let's call it like that, implies reduction of oscillation? Well, it's extremely simple, in fact. This is formulated for a sub-solution and then you decrease the max, but just by plugging minus f, you could have a symmetric result where you increase the mean for a super solution. You okay with that? Super means you reverse the sign in the equation, you reverse my assumption, and everything is reversed. So if you take f a as in the reduction of oscillation lemma, and then let's do a nice rescaling in order to use all the power of the scaling invariance. So I'm going to rescale as follow. Okay, and everything is done on B2, sorry. Inf of f, sorry. So what I'm doing is that I'm taking the sup, I'm taking the inf, I'm taking the midpoint, I'm recentering there, and I'm dividing by the oscillation. So I produce really something. This g now function is valued in minus 1, 1. And it's even better than that. It has oscillation exactly 2. So of course, well, you could protest if the oscillation of f was 0 in B2, but in that case, there's really nothing to prove, okay? So we don't consider that. Because I've just modified f by adding, subtracting constants and multiplying, it's still a solution. So G is still solution, a full solution to the PDE. Then, now I'm considering what happens in B1. Either the mass, I'm calling it a mass for lack of a better word, but let's say either the measure when G is less than 0 is greater than half of B1, or the measure where G is greater than 0 is greater than half of B1. So it's the measure here. Well, one of these has to hold. If in the first case, so let's call that little I, let's call that little 2I. Just going to finish it here. In the first case, you apply In the first case, you deduce that you apply the measure to pointwise to G, and you get that G is less than 1 minus lambda on B1 half. And therefore, because G was greater than minus 1, you get that the oscillation of G on the ball B1 half is less than 2 minus lambda. So it's reduced strictly. And in the second case, you apply your measure to pointwise estimate to minus G. So, which is now also a subsolution. And you get that G is greater than minus 1 plus lambda on B1 half. And therefore, again, the oscillation of G is decreased. Okay, so that's just this. And now the statement that we'll prove next time, just to make the connection, is the next step is the so-called intermediate value lemma of the Giorgi. It's an interesting sort of H1 version of a Taylor expansion argument. It tells you that if G is H1, so it's not really a good way to formulate it for hypoelliptic theory, but let's start with that. If G is H1 in B1, then we can, let me write it down and then I'll stop here. We can bound the measure of where G is between 0 and 1 half below by a certain constant. Of course, if this is 0, it has nothing to do, as always. That we'll discuss next time where it comes from, by the measure of the set where G is greater than 1 half to the 1 half times, to the 2, sorry. To the measure of the set where G is less than 0 to the 2 minus 2 over dimension. Okay. So that's what we're going to prove next time. And this is where trajectories start showing up. So that's, in some sense, the whole goal of the classical theory is for you to understand the key concepts, because if I would start directly with kinetic equations, that will be a little bit, I would have to skip all that and admit a lot of these things. But this is really where we'll start using trajectories to make this sort of argument quantitative for hypoelliptic equations. Why trajectories? Because you want to relate, you want to say that when G is, in order to have values below 0 and value below 1 half, somehow it needs to pass through the intermediate values. So we want to quantify that with trajectories. Okay.
Thank you very much. Are there any questions before tea? I was wondering, in the case of parabolic equation, to show that you gain regularity, imagine there's a counterpart of this method, or how?
Absolutely. So I in some sense, I included the parabolic case in the kinetic case by lack of time, because if I would do the 3 cases, there would be too many repetitions, but it's extremely similar. The main thing is that your this is the way it's usually represented. I mean, not my choice, even like that. You center everything. Time is here. That's my schematic representation of the space variables of your parabolic equation. And now, every time I drew some balls reducing to smaller balls and so on, the picture will look like that. You reduce towards the final time. These are the so-called parabolic cylinders, and this is the way they scale. And there is, all of that is obvious when you start writing it. The scaling between t and x obviously respects the scaling between 1 t derivative and 2 x derivatives, so there is a different exponent.
Okay, so you adjust the size of your domain to make them longer?
No, it means when you scale them, you will scale them by, when you multiply by some factor, r, you will multiply by r squared in t and r in x. Okay. In order to match the equation. It has to be scale invariant. You didn't see that in the elliptic case because all the coordinates had the same number of derivatives. But that's all here. Yeah. And apart from that, more or less everything I said carry on. The viewpoint of Moser is the easiest in some sense for the iteration to, it exactly applies directly to the parabolic case. And, but it's very similar.
Thank you very much. So if there's no more questions, then we'll have tea now. Thank you.